In this unit, we're going to discuss the CPU and the motherboard. You should have already viewed the initial presentation about the chassis and the case. So this picks up on that. We'll talk about the CPU and the motherboard. So we already discussed the information processing life cycle, and we'll come back to this periodically throughout the semester as we relate different ideas or different parts of the server back to this information processing life cycle. And it's helpful to put in perspective everything that we're looking at into this overall process. But we started with input, then we went to processing, output, and storage. And then, of course, we also talked about communication. In this unit, we're going to take a kind of a different look at this information processing lifecycle. We're going to change the names of these a little bit and look at how a processor itself, the CPU, the central processing unit, and how the actual microprocessor carries out its job, how it does, how it actually processes information. So slightly different terms we use. We use fetch. So fetch is sort of like input, and then decode, execute, and store. So fetch, decode, execute, and store. These are the four basic processes that are done by a microprocessor for each instruction. So when we talk about an instruction in a microprocessor, it's carrying out these four basic functions. So if I were to ask you, and by the way, a microprocessor or a CPU has a clock that coordinates all of this. So each tick of that clock, and it's usually at a set pace. So there's a set pace that clock is ticking, and at each tick of that clock, it has to fetch, then decode, then execute, and then store. So to carry out one process or one instruction, it takes 4 clock cycles. The first one it's fetching, the next one is decoding, and it executes, and then it stores. Of course, in reality, the processor doesn't have to be only doing one of these at a time. So it could fetch, on the first clock cycle, the second clock cycle, it could be fetching the next one and decoding the previous one it fetched. And on the third one, it could be executing what it just decoded, decoding what it just fetched, and fetching the next instructions in the next input. So by no means does this have to, do you have to take 4? And in fact, that concept is called pipelining. So when you look at modern microprocessors, sometimes you'll see them talk about pipelining, and that's basically what pipelining is. So let's take a look at how this actually works. How do we go from just having electricity, just these pulses of electricity, the plus and minus 5 volts that we talked about in the previous slide? How do we go from that to actually doing math, doing arithmetic, and and all the cool stuff that our computers do? So of course it all starts with the basic building block of any processor, which is the transistor. So I have a picture on my screen of a transistor. They're quite small. I mean, that one, you could see it if you held it in your hand. It's maybe a couple millimeters. So it does have a little bit of size to it. But of course the ones that are in our microprocessors are much smaller than that. In fact, a modern microprocessor could have millions, if not billions, of these transistors packed inside the little package that we're going to talk about. So how do these little guys actually do arithmetic and math and all that, all that sort of thing? To understand that, it's important to know a little bit about arithmetic and math. Pretty much any mathematical operation, its basic DNA is logic. So and, or, not, with these basic logic, so being able to use basic logic of and or and not, by combining those you can get addition, subtraction, multiplication, division, and then of course from those you can get higher mathematics. So computers, and of course in computing we only have 2 states to work with, 0 or 1, true or false. And when we talk about Boolean logic, that's basically true and false. So if I have, with an and, if you were to draw a truth table for and, if we have a true and a true, then it would be true. But if it's a true and false, it would be false. However, with an or, that would be true. So with that basic Boolean logic, if instead of calling it true and false, we call it 1 and 0, 1 being true, 0 being false, from that basic building block, we can build, we can get to basic arithmetic. So let's take a look at how that works. We'll start with, so this type of transistor that I'm showing you the symbol for is an XOR gate. And by the way, they call them gates. So an operational amplifier or an op amp or a transistor is can have different, different types of transistors have different types of logic, or different little circuits of transistors can have different types of logic. So in this case, let's say we have a little transistor circuit that has two inputs and an output. And when we combine those inputs and outputs, it basically creates an XOR truth table. So if both A and B, so both of those inputs, are false or 0, then S, which in this case stands for sum, so the S would be 0. And if there's a 1, if a 1 exists anywhere, it's going to be a true, or a 1. So that's a basic XOR gate. And likewise, I can take there's a different type of gate. That's an AND gate. So I'm showing you now the symbol for an AND gate, and the truth table looks like this. So for an AND gate, both of the inputs have to be true in order for the output to be true. In this case, we're calling it C, and I'll get to that in just a minute why we're calling that C. But the output in this case, which is C, is only a 1 if everything is true, if both A and B are true, because it's an AND gate. So if we combine these two, we can get what's called a half adder. So if we create a little circuit, and by combining these two gates, we have a half adder. So there's two inputs, A and B, and then we have two outputs, S, which is for sum, and C, which is carryover. So just like any other arithmetic, when you do binary arithmetic, which is what we're doing here, by the way, this is all binary arithmetic because we can only work with ones and zeros in a computer. But with binary arithmetic, there's obviously a lot of carrying going on, because if you add 1 plus 1, you have to carry the 1. So you have to account for that. So let's take a look at, and let's see if we combine these two truth tables, we can basically come up with addition. So take a look at this. If I have two zeros in the first truth table, I have A and B are both 0. The sum is 0, and the carryover is 0, which is correct. If I have a 1 in either A or B, then my sum is going to be a 1, and there's no carryover. So C is 0 on both of those. And then finally, if both are a 1, my sum is a 1, plus I have to carry the 1. So this is basically what a half adder looks like. And you can see the truth table over here for A, B, the sum, and the carryover. And it works. So with this very basic little circuit, I can add 1 and 0. And basically I can add a single, 2 bits. So this is a 2-bit adder. That's pretty much all this can do. I can also make a full adder by adding a few more transistors to the circuit, a few more logic gates to the circuit, and we can get more of a true adder out of this, or a full adder. So all of these little transistors, and by the way, this is only addition, it's very basic addition. If I wanted to add more than just A and B, so if I wanted to have, say, 8 inputs, to add 8 binary digits, 2 sets of 8 binary digits, I would have to have 16 of those inputs, and that would be significantly more transistors, but I can do it. I can scale that up to many, and you can see how, why we need these billions upon billions of transistors in our computers in order to do any, calculations, because we have to have all this advanced logic. And not only that, but we have to have a way to feed a lot of instructions into our processor. So in any event, all of these, by the way, there's the truth table for our full adder. So we have a. Now, by the way, the reason this is a full adder, the first one, all I can do is add 2 binary digits and get the result. This one handles the carry in. So there's both the carry in and the carry out. So there's 3 inputs. There's the A and the B, and then the third input is carry in from the previous instruction, or from the previous addition. So you can kind of string these together to get a to add more and more bits. And of course, doing once you can do addition, doing subtraction, multiplication, and division is arbitrary from there. It's all just arithmetic, but it all has its roots in addition, and really in logic, as we just seen in Boolean logic. So all of these transistors basically get shoved into a tiny little package, which we call our microprocessor, and that's what you see in your computer, the microprocessor. To give you a very basic example of how these work, let's say I have a very basic microprocessor that has 2 inputs, A and B, and we have an instruction, an input for instructions, because we have to tell the processor what to do. Most processors can do a lot more than just add and subtract or something like that. So there are many, many, many different instructions that you can pass into these microprocessors. So you have an A input, a B input, somewhere to input the instructions, and then of course the output, which is the result of the calculation. So if this were an 8-bit processor, you can see here's my 8 leads. I've got 8 leads for my A input, 8 leads for my B input, and then 8 for my instruction, and then I get 8 leads for my output. So if I had the number 101 and the number 102, and I wanted to add those two, of course first I'd have to convert them to binary. But basically, once converted to binary, I can put voltage on each one of these little leads. At -5 for 0, +5 for 1 volt in my A and my B input. And then I decide, what instruction do I want to do? In this case, let's say I wanted to add. And in this particular microprocessor, let's say that the instruction to add is 81. So I have to use 81 on the instruction input in order to tell this microprocessor that I want to add these two together. So I put my 81 on the input for the instruction. And then of course once that happens, the next clock cycle, our microprocessor is going to output the result of that calculation. Now this is only an 8-bit processor, so if I wanted to add large numbers, it would be difficult because we only have up to 256 for both the input and the output, and up to 256 for our instruction set. So that means we only have about 200 and some odd possible instructions for this microprocessor, which is okay for a primitive microprocessor, but most of our computers require millions of different instructions, millions of different things that our microprocessor can do. So obviously we need a lot more than 8-bit. If we step up to 16-bit, then we can get up to 1024. So that means we can add numbers that are up to 1024, but our output can only be up to 1024. By the way, if you try to add numbers that are greater than, where the sum will be greater than 1024, obviously that's going to be an error. You won't be able to do that. So if you were a programmer, you would have to account for that. You have to know that if you have an integer that's going to exceed the maximum, that you have to break it into pieces and do multiple instructions and things like that, which of course slow down our processor. So obviously having more bit depth is advantageous. It allows us to do more with our processor in fewer clock cycles. So we can do more in less clock cycles when we have more bit depth. In this case, 16 bits gets us up to 1024. And then there's 32-bit, which used to be the most common. Of course, now we've got these 64-bit processors, which can handle significantly larger integers or instructions and output and all that kind of stuff. So certainly processors are getting much more powerful, and they're with these 64-bit processors. But this is why 64-bit gives us so much more, so much better performance, even if we don't have. If the processor doesn't run as quickly, we can do more in each clock cycle. So talking about a microprocessor, there's multiple parts of a microprocessor that our book discusses. The control unit, which manages the flow of the program. The execution unit, which does the arithmetic logic. So what you just saw there, the arithmetic logic unit, which does the addition and subtraction and multiplication and division and Boolean logic and that sort of thing. And then the floating point unit, which used to be a separate. Sometimes, back in the old days, you would actually have a separate little chip that did floating point, which is just a way of doing arithmetic on numbers that are not complete integers. So an integer doesn't have a decimal. Floating point numbers are numbers where there's a decimal or a fraction of a number. So 364.5 would be an example of a floating point. And the reason it's called a floating point is the point can move around. It doesn't have to be always 1/10 or 1/100th or 1/1000th. So sometimes you had a separate execution unit for that. And then the register, which is where we do storage and memory in the chip. You'll frequently hear that referred to as L1, L2, and L3 cache. And you usually see the size in L1, L2, and L3 cache. And that's very important for performance. We'll see why in just a few minutes. And then you have execution units or cores of execution units. So you can have a multi-core processor, which of course is very common now. You have quad-core and things like that. In order to take advantage of that, though, you have to have simultaneous multi-threading technology in the operating system. So the operating system has to support that. Talking a little bit more detail about the performance. I talked about cache, and I think it's really important to understand how caching can really affect the performance of a microprocessor. So here's our friend Buzz from our electrical safety slide from the previous unit. And let's say Buzz worked at a factory assembling cars. So, and let's pretend for a moment that Buzz's job is to put the tires on the cars. And the way most microprocessors work now with pipelining, Buzz's job to put those tires on the car is just one step in that cycle. So it's sort of like a factory assembly line. So if the cars are coming down the assembly line and his job is to put tires on the car, here's the tires that he has on the rack next to him. So the first car rolls up to his station and he takes 4 tires off of the rack and puts them on the car, and then that car rolls on and he's got the next car to do. Now there's a problem here, is he only has 2 tires, so he can only do half this car. So he has to go get new tires. Now while he goes to get those new tires, everyone else in this assembly line has to stop. So everything stops while this guy has to go get the tires for him to complete his job. And maybe he goes out to a storage shed and gets those tires. So maybe it's just a few minutes. The line just stops for a few minutes. It doesn't, have a major effect on the factory's output, which is okay. So he goes out and he goes and gets those tires and comes back, and then they can start the line again. But what if he's out of tires from that short-term storage, from that storage shed next to the factory? Now he's got to call the factory and place an order, and he's got to wait for the truck to ship those tires in order for him to refill his inventory to start putting tires on cars again. And if that takes 2 weeks, because the tires are a fairly important part of the car, the entire assembly line has to stop and wait for him to get those tires, which of course is going to drastically affect the output of the factory. So when we talk about performance in a microprocessor, when you see L1, L2, and L3 cache, this is why it's important. Is you need to have, you want to have enough cache space on the processor to handle, sort of temporarily hold the raw materials the processor needs, or the data that it needs in order to do its job. If it runs out of data to do processing and it has to go out somewhere else to get that data, like the memory, the RAM, which we're going to talk about in the next unit, that's going to slow down considerably this process. And of course, if you have to go and get that data from the hard drive, it's going to take even longer. So going out to the storage shed is like going out to RAM, and ordering your tires from the factory and waiting for them to ship is like trying to get data from a hard drive. It's a difference of a couple seconds to put the tires on versus a couple minutes to walk to the storage shed, which would be something like L3 cache or RAM, versus having to go all the way to the hard drive to data, which would be similar to ordering, waiting 2 weeks for the tires to come in from the manufacturer. So memory and cache is important to microprocessor performance. Microprocessor performance is generally measured in MIPS, or millions of instructions per second. Your book has a little blurb about that. MIPS has really kind of become not as important for measuring microprocessor performance. I mean, it does give you a nice raw objective number you could look at, but one thing you have to remember is that simple instructions don't always tell you how well that processor is going to perform. I'll give you an example. If you have an 8-bit processor that can perform, 7 million instructions per second, or I'll make it more reasonable, 74 million instructions per second, it's pretty darn fast. But what if I also had a 32-bit processor which only performs, say, 10 million instructions per second? Even though it's slower, even though it does fewer instructions per second, that 32-bit processor, clearly it's going to outperform the 8-bit processor, because it can do so much more per clock cycle, because we can calculate larger numbers and we have larger instruction sets to work with. So we have, you no longer have to break down processes into primitives. You can do process. If you want to tell if you want to get the value of pi, there might be an instruction to do that instead of having to calculate it yourself through primitive arithmetic. So millions of instructions per second is important, but you also have to make sure you look at all the other things like the clock speed, the bit depth, or how many bits of instructions and input and output you have, which is usually all the same, by the way. If you have a 32-bit processor, it's 32-bit for input, output, and instruction set. And of course the cache. If you if you've got a processor that can do some ridiculously high number of instructions per second, but it doesn't have enough cache, it's going to constantly be waiting to for clock cycles to pull data into cache, which could also slow down the processor. So you got to make sure you've got all of this stuff. Sort of has to be scaled up together. You can't just look at the speed of the processor. So if I asked you in a homework assignment or a test or something, what can you look at when you purchase a microprocessor? When you're looking at the specifications of a microprocessor, you should talk about all of these things and how they all affect the performance of a microprocessor. When you purchase a microprocessor, in our textbook they talk about, by the way, they call that a package. So the little chip itself, all those transistors sort of packed into that little chip, that's called the package. In the old days we had PDIP, or plastic dual inline package, which looks something like this. And it's a very simple older processor. You can see it's a Nintendo processor, probably from the 80s. They're not, not a whole lot of pins on there. We didn't have a whole lot of bit depth in those days. So more modern processors you'll find are PGA, or pin grid array. So they look something like this, and of course that's not a very big processor. There's not very many pins on that. Typically modern processors will have far more pins than what you see there, and those chips sort of nest into the motherboard, as you see here. So that chip would flip. This chip you see on the right flips upside down and just kind of sits inside. All those little pins get nestled into all of those slots in there. Typically they're keyed, so they can only go in one way. You can see in the picture on the left there's a little bump out in the top left side, which would force you to put that chip in the right way. And if you look at the diagram on the right with all the pins sticking up, you'll see that there's different numbers of pins on each side that kind of key it. So it'll only, if you place it on top of the motherboard, it'll only slip in one direction. If you have it the wrong way, it won't go in. So one thing I always tell students when we're assembling computers in class is never force these chips, because those pins bend very easily. They're very small, and they'll bend and once you bend those pins, you can't sit there and bend them back. It would take forever, and it doesn't usually work after that, and they snap off. So you kind of want to just lay it on that receiver and kind of, if you have to, try laying it on there 2 or 3 different ways and see when it falls in. It'll just kind of fall into place, and it won't move around. So once it falls into place, you can stick your finger on the top and move it back and forth, and it won't really move very much. But if it doesn't slip in there quite right, if you put your finger on it and move it, it's going to move a lot back and forth, and you know that you're not properly seated in the motherboard. And of course, when we buy a motherboard, or if we're buying a CPU, we have to make sure that they match. So the motherboard has to support the CPU, or the CPU has to fit into the motherboard that you have. So if you're replacing a CPU in a server, unless you want to replace the entire motherboard, you have to make sure the CPU is going to fit in the slot that you have. And in your textbook, you'll see a diagram, or a table of all the different standards for that, and there are many of them. So it's important to make sure you get the right kind. And of course, one problem is sometimes you'll have an older server that the processor dies for some reason, and you can no longer purchase a processor for that slot. So then you have to upgrade the entire motherboard just to replace the processor. But it does happen. But you'll see the table of all the different processors and their slots and how they fit in, the number of pins and all that sort of thing. This is a diagram, speaking of the motherboard. This kind of leads us right into motherboards. And this is a diagram of the whole motherboard. You can see that CPU receiver kind of right in the middle of the screen there. I'll put a red box around it. So that's where the CPU goes. You also have the memory. So that's the memory to the right of it. Now, of course, that's not L1, L2, L3 cache. That's usually built right onto the microprocessor. But this would be the memory or the RAM that you can install on the computer. You'll also typically have power connectors. So when we talked about power in the previous unit, you saw that long connector with all the wires sticking out of it for the motherboard, and that's where it would plug in from the power supply, which we talked about in the previous presentation. You've also got your connectors for storage. So in this case, you can see there's a bunch of SATA connectors on this motherboard. I see a USB hub connector on there, so a couple different connectors for storage. And then we also have our expansion slots, which we're going to talk about in a couple of units. We're going to talk about expansion cards. So these are cards you can add to the computer. And then you've got your input and output from the motherboard or from the computer. So these are all your ports on the back of the computer: your USB, PS2, FireWire, and IEEE 1394, serial connectors, VGA, DVI, etc., etc. So that motherboard is the main circuit board in the computer. Everything connects to that main circuit board. So the CPU fits in there, your RAM goes in there. Everything that connects to the computer is going to connect to that motherboard. It's sort of the heart of the computer. You can also have a daughter board. These aren't common anymore, but it used to be that you couldn't fit everything into the main circuit board into that motherboard, so you would have daughter boards which would connect either with a ribbon cable, or they would have a special connector for an additional circuit board, and it would be called a daughter board. But those aren't very common anymore. You won't really see that in most modern systems. But what you will still see is a riser card, which is kind of similar to a daughter board, but it's basically a riser is usually a way to connect a card that won't fit in the form factor. So for example, in this picture that you see here, if you had a PCI card that would be too big to fit in the case, so if you take the card and you put it in that slot, it's going to stick straight up, and maybe it's going to be too high, and it won't clear the case. If you recall, when we looked at the sizes of the CPU chassis for servers, we have a 1U server case. Well, 1U is only 1.75 inches tall. And I'm sure most of you have seen PCI cards that are much more than 1.75 inches tall. So if you had to install one of those in a server, typically you'd have to do something like this. You have to get a PCI riser card, and it basically gives you a 90 degree. It just converts that PCI connector 90 degrees to what it is on the motherboard, so that the PCI card can be horizontal as opposed to sticking up vertically and sticking out of the case. So it lets you put a larger card into a 1U or a 2U platform. So we have different form factors. ATX is the older form factor, although it's still kind of considered the standard. It's based on the AT and XT standards for form factors, which are obsolete now. But ATX, so these form factors basically refer to the size, the geometry of the motherboard. So ATX is a standard size. LPX is a little smaller, ITX a little smaller, and BTX obviously is the smallest. And these are the standard form factors. You've also got non-standard form factors, things like laptops, tablets, cell phones. I mean, they all have motherboards, but there's no standard size for those. So they would, there's no standard form factor for those. But if you go out and you buy a server chassis, a 1U server chassis or a 3U server chassis, they're going to tell you which form factor for the motherboard will fit into that server. Typically, with a server, it'd be ATX or LPX. Because they're bigger. Servers, you've got 19 inches wide to work with, and you've got 31 or 38 inches in depth. So you're usually not limited too much in the size. So we don't need to get really small motherboards. But for desktop platforms and things like that, you'll find the smaller form factors.